Welcome back to the channel where we explore the deepest mysteries of reality itself. Today, we're diving into something that will fundamentally change how you see every single thing around you. And I mean everything. The screen you're watching right now, the room you're sitting in, even your own body. Here's the shocking truth that physicists have been grappling with for over a century. Reality doesn't exist until you look at it. I'm not speaking metaphorically. I'm not being poetic. This is actual, experimental Nobel Prize-winning science. When you're not looking at something, it exists in a blurred state of all possible configurations at once. And light, photons, observation, they're the trigger that collapses infinite possibility into singular fact. Think about that for a second. Right now behind you, the room you're not looking at might not actually have a definite configuration until you turn around. The atoms in the wall, the objects on your desk, they're hovering in a quantum superposition of all possible states. And the moment light bounces off them and hits your eyes, reality snaps into a single definite state. This isn't philosophy. This isn't spiritual mysticism. This is what the mathematics and experiments are telling us about the fundamental nature of existence. And by the end of this video, you're going to understand exactly why light might be the most important thing in the universe. Not because it lets us see, but because it might literally be creating the reality we see. Before we dive deeper into this rabbit hole, do me a favor. Hit that like button if you're ready to have your mind completely reconstructed today. And drop a comment telling me what country you're watching from and what time it is there right now. I love seeing our global community come together to explore these ideas. And subscribe if you haven't already, because we're about to embark on a journey that challenges everything you think you know about existence itself. Let's start with something simple, something you learned in school. Light is electromagnetic radiation. It travels at 299,792,458 meters per second. It behaves like both a wave and a particle. Easy, right? We've known this stuff for decades. But here's where it gets weird immediately. In 1801, a British polymath named Thomas Young performed what's now called the double-slit experiment. He took a light source, shined it through two narrow slits, and watched what pattern emerged on a screen behind those slits. What he saw was an interference pattern, alternating bands of light and dark. This proved light was a wave, because waves interfere with each other. When two wave peaks meet, they create a brighter band. When a peak meets a trough, they cancel out, creating darkness. Makes sense so far. Light is a wave. Waves interfere. Elementary physics. But then quantum mechanics came along and ruined everything. In the 1920s, physicists started doing this experiment with individual photons, sending them through one at a time. Now, here's the question that should bother you. If you send one photon through the slits, one single particle of light, which slit does it go through? Left or right? It has to be one or the other, right? Wrong. Impossibly, insanely, universe-breakingly wrong. When you send individual photons through the slits one at a time, they still create an interference pattern. Over time, as thousands of individual photons hit the screen, they build up the same striped pattern. But here's the thing. For waves to interfere, they need something to interfere with. A single photon can't interfere with itself. Or can it? The mathematics says yes. Each individual photon goes through both slits simultaneously. It exists as a wave of probability, spreading out to encompass both paths at once. It interferes with itself. The single photon is in a superposition, existing in multiple states at the same time. When it hits the screen, it collapses into a single point, one definite location. But which location it chooses follows the probability pattern created by the wave interference. Think of it like this. Imagine you're at a fork in a road. Common sense says you go left or you go right. But quantum mechanics says you do both. You simultaneously take the left path and the right path. You exist in both places at once. And only when someone at the destination looks to see which path you took does the universe decide which one you actually took. That's already mind-bending. But we're just getting started. In 1978, a physicist named John Wheeler proposed something even more disturbing. He called it the delayed choice experiment. Wheeler asked, what if we don't decide whether to measure which slit the photon goes through until after it's already passed through the slits? Does the photon know in advance whether we're going to look? The experiment goes like this. Send a photon through the double slits. But this time, we have detectors that can tell us which slit the photon went through. However, we don't turn these detectors on until after the photon has already passed the slits, but before it hits the final screen. So the photon has already chosen whether to be a wave going through both slits or a particle going through one slit. Our measurement happens too late to affect that choice, right? Wrong again. When Wheeler's team actually performed this experiment, they found something impossible. If they decided to measure which slit the photon went through, even after it passed the slits, the photon behaved like a particle and went through only one slit. No interference pattern appeared. If they decided not to measure, the photon behaved like a wave, went through both slits, and created an interference pattern. The photon's past behavior changed based on a future measurement decision. Let me say that again, because it's crucial. The experimenter's choice of whether to observe the photon changed what the photon had already done in the past. The future reached back and altered the past. The photon retroactively decided whether it had been a wave or a particle based on whether someone was going to look at it later. This isn't time travel in the science fiction sense, but it is something equally profound. It suggests that observation, specifically the interaction with light and photons, doesn't just reveal reality. It determines reality, potentially even backwards through time. Now you might be thinking, okay, this is weird quantum stuff with photons, but surely this doesn't apply to real, everyday objects. Surely my coffee cup isn't in multiple places at once until I look at it. And you'd be wrong to think that. The reason you don't see quantum effects in everyday life isn't because they don't apply to large objects. It's because large objects are constantly being observed by the environment around them. Every single photon bouncing off that coffee cup, every air molecule bumping into it, every thermal radiation emission, these are all measurements that collapse the quantum superposition. The cup can't maintain a state of being in multiple places because it's being measured billions upon billions of times per second by its environment. But remove those environmental interactions, and even large objects exhibit quantum behavior. In 2010, a team at the University of California, Santa Barbara, led by Andrew Cleland, managed to create a tiny mechanical resonator, barely visible to the naked eye, and cool it down to near absolute zero to eliminate environmental interference. They got this object, made of trillions of atoms, to exist in a quantum superposition. It was literally vibrating and not vibrating at the same time until they measured it. The line between the quantum realm and the everyday world isn't a line at all. It's a gradient of how much observation is happening. And light, photons, are the primary mechanism of that observation. So here's where we are so far. Light doesn't just let us see things. Light, through its interaction with matter, forces matter to take on definite properties. Without light, without observation, things exist in multiple states simultaneously. The universe is a fog of probabilities. Light turns those probabilities into facts. But this raises an enormous question that's going to occupy us for the next section. If observation creates reality, and no one's observing most of the universe, what state is most of reality actually in? And before the first conscious observers evolved, before anything could observe anything, what was the state of the entire cosmos? The answer is going to challenge your understanding of time, space, and existence itself. And it involves something called the observer problem, which has split physics into warring camps for nearly 100 years. We'll get into that in a moment. But first, let me know in the comments. Have you ever thought about what happens to reality when you're not looking at it? Does your bedroom exist when you're at work? I know it sounds ridiculous, but by the end of this video, you might not be so sure. Let's talk about the observer problem. It's been the elephant in the room since quantum mechanics was first formulated in the 1920s. Niels Bohr, Werner Heisenberg, and the Copenhagen interpretation crowd said, "Look, the math works. Particles exist in superposition until measured. Measurement collapses the wave function. Don't ask what's really happening. Just shut up and calculate." But not everyone was satisfied with that answer. Albert Einstein famously pushed back against this idea his entire life. He couldn't accept that the moon only exists in a definite state when someone looks at it. He wrote to a colleague, "Do you really believe the moon isn't there when nobody looks?" For Einstein, there had to be some underlying reality, some definite state things were in, whether or not we observed them. So in 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper challenging quantum mechanics. They described a thought experiment, later refined by David Bohm, that went like this. Create two particles that are quantum entangled, meaning their properties are linked. Separate them by a large distance. Now measure one particle. Quantum mechanics says this measurement instantly determines the state of the other particle, regardless of the distance separating them. Einstein called this spooky action at a distance, and argued it proved quantum mechanics was incomplete. Information can't travel faster than light, so how could measuring one particle instantly affect another particle light years away? There must be hidden variables. Einstein argued, predetermined properties we just can't see that determine the measurement outcomes. For decades, this remained a philosophical debate. But then, in 1964, an Irish physicist named John Stuart Bell changed everything. Bell figured out a way to test whether Einstein was right. He derived a mathematical inequality, now called Bell's inequality, that would be satisfied if Einstein's hidden variables existed, but violated if quantum mechanics was correct. And then came the experiments. In the 1970s and 80s, physicists like John Clauser and Alan Aspect performed increasingly sophisticated tests of Bell's inequality. And the results were unambiguous. Bell's inequality was violated. Quantum mechanics was right. Einstein was wrong. There are no hidden variables determining particle states before measurement. The universe genuinely is indeterminate until observation collapses the possibilities. Alan Aspect, along with John Clauser and Anton Zeilinger, won the Nobel Prize in Physics in 2022 for definitively proving this through experiments that closed all the loopholes Einstein might have exploited. The experiments showed that entangled particles really do influence each other instantaneously across any distance. When you measure one particle and collapse its wave function, the other particle's wave function collapses simultaneously, even if it's on the other side of the galaxy. Now, information doesn't actually travel faster than light in this process, so it doesn't violate relativity. You can't use entanglement to send messages. But what it does prove is that reality is fundamentally non-local. The universe is not made of separate, independent things sitting in definite states. It's an interconnected web where observation in one place can instantaneously affect states in another place. And here's what that means for light and observation. When a photon from a distant star, which has been traveling through space for thousands or millions of years, finally hits your eye, that photon has been in a state of superposition for its entire journey. It's been every possible wavelength, every possible path. Only when it interacts with the rods and cones in your retina does it collapse into a definite state. The photon's properties were undefined for millions of years, and your eye created them. Think of it like this. You're watching a movie, but the movie doesn't have a script until the moment you watch it. The film exists as every possible movie simultaneously. Only your act of watching forces it to be one particular movie. And everyone watching sees a movie that's consistent with the movie everyone else sees. because the observation itself creates the consistency. This isn't just an academic curiosity. It has profound implications. Anton Zeilinger, one of those Nobel Prize winners, has used quantum entanglement to develop quantum cryptography, a method of sending messages that's theoretically impossible to hack, because any observation by an eavesdropper would collapse the quantum states and reveal the intrusion. The indeterminacy of reality until observation becomes a security feature. But let's zoom out from the applications and look at the bigger picture. If observation creates definite reality, and most of the universe isn't being observed by anything, what state is it in? One answer comes from the many worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957. Everett said, "What if the wave function never collapses? What if every possible outcome of every quantum measurement actually happens, but in different branches of reality? When you measure that photon going through the double slits, the universe splits. In one branch, you measure it going through the left slit. In another branch, you measure it going through the right slit. Both happen. You just only experience one branch." In this interpretation, light doesn't turn possibility into fact. Light creates a branching tree of infinite realities, all equally real, all happening simultaneously. Every possible history exists. Every time a photon could go left or right, the universe divides into versions where it did each. The number of parallel universes is incomprehensibly vast, increasing by trillions upon trillions every microsecond. This interpretation has gained significant traction among physicists in recent decades because it takes the math of quantum mechanics seriously without adding any extra assumptions about wave function collapse. The equations naturally describe a branching multiverse. No collapse needed. But there's another interpretation that's even more radical. It's called quantum Bayesianism, or QBISM for short, developed by physicists like Carlton Caves and Christopher Fuchs. Cubism says quantum states aren't describing the real physical state of the world. They're describing your personal state of knowledge about the world. The wave function is subjective. It's your probability assessment. When you observe a particle and the wave function collapses, that's not a physical event. That's you updating your knowledge. In this view, quantum mechanics isn't telling us about reality itself. It's telling us about the limits of what we can know about reality. Different observers can have different wave functions for the same system because they have different knowledge. Reality exists independently, but we can only ever describe our relationship to it, our knowledge of it, which is fundamentally limited and probabilistic. So does light turn possibility into fact? Cubism would say no. Light updates your information about what fact was always there. Many worlds would say light creates all facts simultaneously in different branches. The Copenhagen interpretation would say yes, light literally collapses possibility into fact. And here's the thing. We don't know which interpretation is correct. They all make the same experimental predictions. We can't design an experiment to distinguish between them because they're all consistent with the mathematical framework that gives us the right answers. What we do know is this: light is the primary way information travels in the universe. Every observation you make, every piece of information you receive about the world around you, comes to you via photons. Light mediates your relationship with reality. Whether that light is creating reality, revealing reality, or branching reality, it's the mechanism by which the indefinite becomes definite from your perspective. And that brings us to perhaps the most disturbing question of all, which we're going to explore in the next section. If observation is required to make things definite, and if consciousness is required for observation, then is consciousness required for reality to exist? Did the universe only come into definite existence when the first conscious beings evolved to observe it? And if so, what came first, the observers or the universe they observe? This is called the consciousness problem, and it's where physics, philosophy, and maybe even spirituality collide in the strangest ways imaginable. Drop a like if your brain is already starting to hurt, because we're about to go even deeper. The consciousness problem is where a lot of physicists get uncomfortable. Because once you start asking whether consciousness is necessary for observation to collapse wave functions, you're leaving the tidy world of mathematics and entering murky philosophical waters. And yet, the question is unavoidable. Here's the issue. In quantum mechanics, we say measurement collapses the wave function. But what counts as a measurement? Does a measuring device count? Does the device need to be connected to a conscious observer? Or is consciousness itself doing something special? Erwin Schrödinger illustrated the problem with his famous thought experiment about a cat in a box. You probably know this one. You put a cat in a sealed box with a radioactive atom that has a 50% chance of decaying in an hour. If it decays, it triggers a device that kills the cat. If it doesn't decay, the cat lives. According to quantum mechanics, until you open the box and observe the system, the atom is in a superposition of decayed and not decayed states, which means the cat is in a superposition of dead and alive simultaneously. Schrödinger proposed this to show how absurd the Copenhagen interpretation was. Obviously, the cat is either dead or alive, even if we don't look. The cat itself is an observer. The cat knows whether it's alive or dead, right? But that just pushes the question back. Is the cat's observation sufficient to collapse the wave function? Or does it require a human observer to look at the cat? Some interpretations suggest that consciousness really is special, that only conscious observation can collapse wave functions. One of the founding fathers of quantum mechanics, Eugene Wigner, took this idea seriously. In 1961, he proposed an extension of Schrödinger's cat called Wigner's friend. Imagine Wigner's friend is in the lab, measuring a quantum system. From the friend's perspective, the measurement happens, the wave function collapses, and there's a definite result. But Wigner is outside the lab. From Wigner's perspective, the entire lab, including his friend and the measurement device and the quantum system, are all in a superposition until Wigner opens the door and looks. So from the friend's perspective, the wave function collapsed. From Wigner's perspective, it hasn't. Who's right? Do different observers have different realities? In 2019, a team of physicists led by Massimiliano Proietti actually performed an experimental version of Wigner's friend using photons as the friends. They showed that, in a sense, both perspectives are correct, but they're incompatible. You can't reconcile the view from inside the lab with the view from outside in a single objective reality. This suggests that observer-dependent reality is not just philosophical speculation. It's experimentally verified weirdness. Now, most physicists don't think consciousness itself is special. They think any interaction that transfers information qualifies as a measurement, conscious or not. The environment is constantly measuring everything through a process called decoherence. Photons bouncing off objects, air molecules colliding with surfaces, heat radiating, all of these interactions collapse quantum superpositions without requiring consciousness. But here's where it gets wild. If we accept that environmental decoherence is constantly collapsing wave functions, creating definite reality, then we have to ask, when did this process begin? At the Big Bang, the entire universe was in an incredibly hot, dense, highly entangled quantum state. Everything was interacting with everything. The universe was observing itself, in a sense, from the very beginning. But let's go back further. What about the Big Bang itself? What was the state of the universe before the first moment of time? According to quantum cosmology, the universe itself emerged from a quantum fluctuation, a wave function that included all possible universes. Something caused that wave function to collapse into our particular universe with our particular laws and constants. What was the observation that collapsed it? This is where you get really speculative theories. Some physicists, like John Wheeler in his later years, proposed the participatory anthropic principle. The idea is that conscious observers in the universe, by observing the universe and collapsing its wave function in the present, are retroactively collapsing the wave function of the entire history of the universe, including the Big Bang itself. In other words, our observations now are reaching back through time and creating the specific history that led to us. The universe exists in a self-consistent loop where observers create the history that created the observers. The future determines the past, which determines the future. Think of it like this. You're playing a video game where the world only renders as you explore it. The areas you haven't visited yet don't exist in any definite form. They're just probabilistic code. When you walk into a new area, the game generates it. But it generates it in a way that's consistent with everything you've already seen. The history is created retroactively to fit the present. In this view, the universe before observers is like the video game before the player arrives. It's not that it doesn't exist. It's that it exists as a superposition of all possible histories. And the act of observation, mediated by light carrying information from the past to the present, collapses those possible histories into one consistent timeline. This is mind-bending stuff, and I should emphasize that this is highly speculative. Most physicists focus on describing how quantum mechanics works within the universe we can observe and test, but the implications are unavoidable. If observation collapses wave functions, and if the past is part of the quantum state, then observation affects the past. And light is the carrier of those observations. Every photon that reaches your eye from a distant star has traveled for years or centuries or millions of years. Until that photon interacts with your eye, its quantum state isn't definite. The path it took, the exact moment it was emitted, all of this exists in superposition. Your observation retroactively determines the photon's history. Now, does this mean you personally are creating the universe's history? Not exactly. The observations that matter for cosmic scale wave function collapse are the collective observations of all possible observers, all interactions, all decoherence events throughout space and time. You're one tiny part of an incomprehensibly vast network of observation and interaction that's constantly collapsing quantum possibilities into classical certainties. But you are a part of it. Your observations do matter. Every time light enters your eyes and collapses a photon's wave function, you're participating in the universe's act of self-observation. You're contributing to the process by which possibility becomes fact. Before we go further, let me ask you this. Do you believe consciousness is special? That there's something about awareness that's different from mere physical interaction? Or do you think consciousness is just another physical process, no more special than a rock? Drop your thoughts in the comments. This isn't just abstract philosophy. It's a question that might have testable answers someday. And if you're enjoying this deep dive, make sure you're subscribed and hit the bell icon so you don't miss future videos where we explore the edges of human knowledge. We're about to enter the section where things get even stranger, because we're going to talk about how light doesn't just observe reality, it creates the structure of space and time itself. Let's talk about what light really is from the perspective of special relativity, Einstein's theory that revolutionized our understanding of space and time. Because light isn't just special in quantum mechanics, it's special in relativity too. And when you combine these two theories, you get a picture of reality that's almost impossible to wrap your head around. In 1905, Einstein published his special theory of relativity, which starts with two simple postulates. First, the laws of physics are the same in all inertial reference frames, meaning anyone moving at constant velocity should see the same physical laws. Second, the speed of light in a vacuum is constant for all observers, regardless of their motion or the motion of the light source. That second postulate is bizarre. It means if you're standing still and shine a flashlight, the light travels away from you at 299,792,458 meters per second. But if you're in a spaceship traveling at 90% the speed of light and shine a flashlight forward, the light still travels away from you at 299,792,458 meters per second. Not at 90%, the speed of light plus the speed of light. Just the speed of light. How is that possible? How can the light's speed be the same whether you're moving or not? The answer is that time and space themselves are flexible. Time dilates and space contracts depending on your velocity. If you're moving very fast, time runs slower for you relative to someone standing still. Distances contract in your direction of motion. These aren't optical illusions. They're real physical effects confirmed by countless experiments. But here's what that means for light itself. From the perspective of a photon, traveling at the speed of light, time doesn't pass at all. The moment a photon is emitted from a star and the moment it is absorbed by your eye are the same instant from the photon's perspective. The photon doesn't experience duration. For the photon, its entire existence, which might span millions of light years and millions of years from our perspective, happens in zero time. Similarly, from the photon's perspective, space is contracted to zero in its direction of travel. The distance between the star and your eye doesn't exist from the photon's frame of reference. The photon is emitted and absorbed at the same location and time from its own perspective. Think of it like this. Imagine you're the photon. You leave a star in a distant galaxy. From your perspective, you instantaneously arrive at Earth. No time passed, no distance traveled. But from Earth's perspective, millions of years passed and you traveled millions of light years. Both perspectives are equally valid. Reality depends on your reference frame. This has profound implications for how we understand light's role in the universe. Light connects events that are separated in space and time from our perspective, but are the same event from light's perspective. Light doesn't experience the separation between here and there, between past and future. Light exists in an eternal now, connecting all points in space-time that it touches. And here's where it gets really deep. The entire structure of space-time, the fabric of reality itself, is defined by light. In relativity, we draw space-time diagrams where the possible paths of light, called light cones, define what events can influence what other events. Events inside your past light cone can affect you because light from those events has had time to reach you. Events outside your past light cone cannot affect you because light from them hasn't reached you yet. Similarly, you can only affect events in your future light cone, events that light from you can reach. The structure of causality, what can cause what, is entirely determined by light's path through spacetime. Light doesn't just reveal the structure of spacetime. Light defines it. Now let's bring quantum mechanics back into the picture. In quantum field theory, which combines quantum mechanics with special relativity, particles are understood as excitations of fields that permeate all of space. The photon is an excitation of the electromagnetic field. This field exists everywhere, at every point in space and time, vibrating and fluctuating at the quantum level. When you emit a photon, you're creating a ripple in this field. The ripple propagates outward at the speed of light. When another particle absorbs the photon, the ripple collapses. But before the absorption, the photon's path isn't definite. It's in a superposition of all possible paths. This is the famous path integral formulation developed by Richard Feynman in the 1940s. Feynman showed that to calculate the probability of a photon going from point A to point B, you have to sum over all possible paths the photon could take, including paths that go backward in time, paths that loop around, paths that take absurd detours. Every path contributes to the final probability amplitude. The photon doesn't take one path. It takes all paths simultaneously until observation forces it to retroactively have taken a specific path. Think of it like this. You're walking from your house to the store. Common sense says you take one path, probably the shortest one. But quantum mechanics says you take every possible path simultaneously. You walk through your neighbor's yard, you take a detour to the moon. You go backward in time and forward again. All of these paths interfere with each other, and the interference pattern determines where you actually end up. The most likely result is the classical path, but the other paths all contribute tiny amounts. For photons, this is reality. Light doesn't travel from A to B along a single path. It travels along all paths. The superposition of all these paths creates the final probability of where the photon will be detected. And here's the kicker. Those paths include paths where the photon travels faster than light, or even backward in time. In the mathematics, these paths contribute to the final answer. They're not just hypothetical. They're part of how photons actually behave. Of course, when you account for all the paths and do the interference, the contributions from faster than light and backward time paths mostly cancel out, leaving the classical light speed forward time path as the dominant contribution. But the other paths are still there, still real in the quantum sense. This is why particles like electrons can sometimes appear on the other side of energy barriers they shouldn't be able to cross, a phenomenon called quantum tunneling. The electron's wave function includes paths that go through the barrier, even though classically it doesn't have enough energy to do so. When you sum over all paths, including the impossible ones, sometimes the particle ends up where it shouldn't be. Light does the same thing. Photons can tunnel through barriers. In certain experimental setups, photons appear to travel faster than light over short distances by quantum tunneling through a barrier. Of course, no information actually travels faster than light. The overall speed averages out, but locally, temporarily, the photon takes a shortcut through the superposition of all possible paths. What this tells us is that the speed of light isn't really a speed limit in the quantum sense. It's more like an average, a dominant path in the sum over all paths. The universe explores all possibilities, including ones that violate relativity, but when all the probabilities are summed, relativity emerges as the statistically dominant behavior. Light is the mechanism by which the quantum realm transitions to the classical realm. Light carries information, and information is what collapses superpositions. Light connects distant points in spacetime, enabling causality. Light defines the structure of spacetime itself through light cones and the invariance of its speed. In a very real sense, light is the bridge between possibility and actuality. It's the medium through which the indeterminate quantum world becomes the definite classical world we experience. Without light, without the electromagnetic interaction, the universe would be a very different place, perhaps a place where nothing could ever become definite. Are you starting to see how deep this rabbit hole goes? We're only halfway through, and already we've seen that reality might not exist until observed, that observation can affect the past, that light experiences no time or space, and that particles take all possible paths, including impossible ones. If you're still with me, you're either a physics geek or someone who genuinely wants to understand the nature of existence. Either way, I appreciate you. Let's keep going. Next, we're going to explore what happens when you look at light from the perspective of general relativity, Einstein's theory of gravity. Because if special relativity showed us that light defines the structure of spacetime, general relativity shows us that light creates spacetime. And I mean that literally. The energy of light warps the fabric of space and time. And in the right conditions, light can create matter, and matter can create light in an eternal dance that might explain why anything exists at all. General relativity, published by Einstein in 1915, describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. Massive objects like stars and planets warp spacetime around them, and other objects move along the curved paths, what we call geodesics, through that warped spacetime. This warping is what we experience as gravity. This has profound implications for the relationship between consciousness, observation, and reality. If conscious experience is constructed retroactively, then the reality you experience is a model, a simulation your brain creates based on sensory input, including light. The photons collapse quantum superpositions when they hit your retina, but the reality you consciously experience is created moments later by your brain's processing. You're not experiencing reality directly. You're experiencing a model of reality that your brain constructs based on information carried by light. And that model, that conscious experience, is what we call observation. It's emergent from the physical processes, but it's also something more. It's qualia, subjective experience, the felt sense of what it's like to see light, to experience color, to perceive the world. And we still don't fully understand how physical processes give rise to qualia. This is the hard problem of consciousness, articulated by philosopher David Chalmers. Why does information processing feel like something? Why is there subjective experience at all? We can explain the mechanisms of how the brain processes information, but we can't explain why that processing is accompanied by experience. Some thinkers, like Chalmers and others, propose that consciousness might be a fundamental feature of reality, like mass or charge. In this view, called panpsychism, even simple systems have some primitive form of consciousness or experience. Complex systems like brains have rich, integrated consciousness. Simple systems like electrons have minimal, unintegrated micro-experiences. If this were true, then observation wouldn't be something that emerges only in complex systems. It would be present, in some minimal form, everywhere. Every interaction, every information transfer would have some experiential aspect. And light, as the primary carrier of information, would be the primary mediator of these micro-experiences throughout the universe. This is highly speculative philosophy, not established science. But it points to a deep connection between information, observation, and experience that we're only beginning to explore. Light carries information. Information collapses superpositions. Observation creates definite reality. Experience accompanies information processing. And consciousness integrates information into unified models of reality. All of these processes are connected, and light is the thread that ties them together. Without light, information couldn't travel. Without information transfer, observation couldn't happen. Without observation, quantum superpositions wouldn't collapse into classical reality. Without classical reality, complex structures like brains couldn't exist. Without brains, consciousness as we know, it couldn't arise. And without consciousness, there'd be no one to ask these questions. It's a loop, a strange loop, as Douglas Hofstadter would say, where each level both emerges from and gives meaning to the other levels. Light creates the conditions for observation. Observation creates definite reality. Definite reality allows complexity. Complexity enables consciousness, and consciousness observes light, completing the circle. Are you seeing the pattern? Everything connects. Physics, information theory, biology, neuroscience, philosophy, they're all describing different aspects of the same underlying process. The process by which possibility becomes fact, mediated by light and observation. We're almost at the end of this journey, but we have 2 more sections to go. First, we're going to personalize this. We're going to talk about what all of this means for you, for your life, for your perception of yourself, and your place in the cosmos. And then we'll wrap up with a conclusion that ties everything together and gives you a new framework for thinking about existence itself. Stay with me. We're in the home stretch. And if you've made it this far, you're part of a select group of people who are willing to grapple with the deepest mysteries of reality. That's worth celebrating. Give yourself a like. You've earned it. Let's make this personal. Because all of this abstract physics and philosophy, it's not just academic. It has direct implications for how you see yourself and your relationship to the universe. And I think when you really internalize what we've discussed, it can be genuinely life-changing. First, let's talk about your observations. Every moment of your life, you're observing the world. Light is entering your eyes, collapsing quantum superpositions, creating definite reality from probabilistic possibility. You're not a passive recipient of a pre-existing reality. You're an active participant in the creation of reality. Now, before this sounds too new agey, let me be clear. You're not creating reality through wishful thinking or manifestation or any of that. The physical processes we've discussed don't care about your desires or intentions. The wave function collapses according to mathematical laws, not according to what you want to happen. But you are genuinely affecting reality through observation. The specific facts that become definite, the specific history that your observations retroactively select from the superposition of possible histories, these are influenced by what you observe and when you observe it. You're collapsing wave functions constantly, simply by existing and interacting with the world through light and other interactions. And here's what that means practically. The reality you experience is genuinely different from the reality anyone else experiences. Not just psychologically, not just in terms of interpretation, but physically. The wave functions you collapse aren't the same wave functions others collapse, because you're not in the same location, looking at the same things, at the same times. In the many worlds interpretation, you're constantly branching into parallel versions of yourself, each experiencing a different branch of reality. In the Copenhagen interpretation, your observations are creating facts that didn't exist before you looked. In cubism, your quantum state descriptions are personal to you, representing your knowledge and your relationship to reality. No matter which interpretation is correct, the conclusion is the same. Your individual perspective on reality is unique, not just subjectively, but objectively. You're not seeing the same universe as anyone else. You're seeing your universe, the one your observations have created or selected or defined. This should be empowering. It means you matter. Your existence, your observations, your participation in reality, these aren't incidental. They're part of the process by which the universe becomes definite. You're helping to create the universe by observing it. But it's also humbling, because everyone else is doing the same thing. Every conscious being, every observer, every system that causes decoherence, they're all participating in the same process. The universe isn't being created by you alone. It's being co-created by the vast network of all observers, all interactions, all decoherence events everywhere and everyone. You're one note in an unimaginably complex symphony. Your note matters. The symphony wouldn't be the same without it, but it's still just one note among countless others. Now let's talk about light and your perception. Everything you see is light that has entered your eyes. That light has traveled through objects in your environment, carrying information about those objects' properties, position, color, motion. But remember, from the light's perspective, no time has passed. The photon was emitted and absorbed in the same instant. So in a sense, when you see something, you're in direct, immediate contact with it, mediated by light. The time delay, the fact that it takes time for light to travel from the object to your eye, is only relevant from your perspective and the object's perspective. From the light's perspective, there is no separation, no delay. The emission and absorption are one event. This means that light connects you instantaneously to everything you observe, from light's own frame of reference. The universe isn't a collection of separate things with space and time between them. It's a network of events connected by light, and those connections are immediate and timeless from the light's perspective. You are not separate from the things you observe. You're entangled with them through the light that connects you. Every photon that enters your eye was part of the object it came from, carried energy and information from that object, and is now part of you as your retina absorbs it. The boundaries between you and the world are more permeable than they seem. And here's something beautiful. The light that enters your eyes is the same light that's been cycling through the universe since the Big Bang. Photons are fundamental particles. They don't age, they don't decay. A photon emitted from the first stars billions of years ago, if it reaches your eye today, is the same photon, unchanged. The light you see is ancient, eternal, connecting you to the deep past of the cosmos. And when you emit light, when your body radiates infrared heat, or when you turn on a flashlight, those photons go out into the universe and potentially continue forever. Light from Earth has been traveling outward into space for billions of years. If there are aliens light years away, they could be seeing light from Earth's ancient past right now. They could be observing Earth as it was millions of years ago, seeing dinosaurs if they have powerful enough telescopes, seeing early humans, seeing ancient civilizations. All that light is still out there, carrying information about Earth's history. And in the future, beings even farther away might see light from this moment, from right now. Your existence, the light reflecting off you and radiating from you, is being recorded in the light that travels outward from Earth. You're part of the universe's history, permanently encoded in the light that's leaving right now. This is a kind of immortality, not of your consciousness or your body, but of the information about your existence. Every moment of your life emits light, and that light carries information outward into the cosmos forever. The universe remembers you through light. Now let's talk about meaning and purpose. If reality is being co-created by observation, if your observations genuinely matter to the structure of reality, does that give your life meaning? Does it give you purpose? From a purely physical standpoint, no. The universe doesn't care about you specifically. The wave function collapses according to physical laws, not according to narrative meaning. There's no cosmic purpose written into the laws of physics. But from an existential standpoint, yes, you get to create meaning. You get to choose what to observe, what to pay attention to, how to interpret and respond to your observations. You're not just passively receiving reality. You're actively participating in its creation. Every choice you make about what to look at, what to focus on, what to value, these choices shape your experience of reality. They don't change the underlying physical laws, but they determine which aspects of reality you observe and how you relate to them. You're the author of your own experiential reality. And because conscious observation seems to be special in that it creates rich, integrated models of reality rather than just simple information transfer, your conscious experience might be a rare and valuable thing in the universe. Most of the universe is unconscious matter and energy, collapsing wave functions mindlessly. But you're a pocket of conscious observation, creating a vivid, meaningful model of reality. That makes you special, not in a grandiose, ego-inflating way, but in a humble, awe-inspiring way. You're part of the universe that has become aware of itself. You're the mechanism by which the universe observes itself and creates meaning from observation. Carl Sagan said it beautifully. We are a way for the cosmos to know itself. Every time you observe the world, every time you look at the stars or watch a sunset or see the face of someone you love, the universe is observing itself through you. Light from the cosmos enters your eyes, collapses superpositions, creates definite facts, and those facts become part of your conscious experience. The universe becomes aware of itself through your awareness. And when you share your observations, when you communicate with others, when you create art or write or teach, or simply tell someone what you see, you're adding your observations to the collective human model of reality. You're contributing to the shared project of understanding and experiencing the cosmos. This is profoundly meaningful. You matter. Your observations matter. Your consciousness matters. Not because some external authority says so, but because the physics and mathematics of reality place you at the center of the process by which possibility becomes fact. So what should you do with this knowledge? How should it change your life? I think it should make you more present, more attentive to your observations. When you look at something, really look. Recognize that you're participating in the collapse of quantum superpositions, the creation of definite reality. Your observation is not trivial. It's the mechanism by which the indefinite becomes definite. It should make you more curious. Every observation reveals something about the universe's structure, about the laws governing reality. Pay attention. Ask questions. Seek to understand. You're not just a consumer of reality. You're an investigator, an explorer, discovering the universe through your observations. It should make you more connected. You're not separate from the universe. You're part of it. The light you see is the same light that filled the early universe. The atoms in your body were forged in stars. The observations you make are linked to observations throughout space and time through the structure of space-time and the web of causality. You're connected to everything, and it should make you more responsible. If your observations help create reality, then what you choose to observe matters. What you pay attention to, what you value, what you look for, these choices shape your experiential reality and contribute to the collective human reality. Choose wisely. Observe with intention. Before we move to the final section, let me ask you one more time. Has this changed how you see yourself? Do you feel more connected to the universe? More aware of your role as an observer? Let me know in the comments. And make sure you're subscribed, because we're about to bring everything together in a conclusion that will give you a new framework for understanding existence. We've been on a long journey together. We started with the shocking revelation that reality might not exist until observed. We explored the double-slit experiment, delayed choice experiments, quantum entanglement, and the observer problem. We examined how light experiences no time or space, how it defines space-time, and how it creates matter through pair production. We discussed decoherence, emergence, and consciousness. And we personalized it, exploring what all of this means for you. Now, let's bring it all together and answer the question we started with. Does light turn possibility into fact? The answer, as you've probably realized, is yes. But it's a nuanced yes that requires us to understand what we mean by possibility, fact, and light. In quantum mechanics, possibilities are represented by the wave function, a mathematical object that describes the probability amplitude of all possible states of a system. As long as the wave function remains coherent, the system exists in a superposition of all these possible states simultaneously. This is what we mean by possibility. It's not that we don't know which state the system is in. It's that the system genuinely is in all states at once. A fact is what emerges when the wave function collapses. The superposition resolves into a single definite state. The many possibilities reduce to one actuality. This is what we experience as reality, as definite classical facts about the world. And light, photons, electromagnetic radiation is the primary mediator of this transition. Light carries information. When a photon interacts with a quantum system, it entangles with that system, creating correlations between the photon state and the system state. When that photon is absorbed by a detector or an eye or another atom, the information is transferred, the entanglement spreads to the environment, decoherence occurs, and the wave function effectively collapses. So yes, light turns possibility into fact by mediating observation, by carrying information, by entangling systems with their environments, by causing decoherence. Light is the mechanism by which the quantum realm becomes the classical realm. But there's a deeper answer too. Light defines the structure of space-time through the invariance of its speed and its role in determining light cones and causality. Light creates matter through pair production. Light carries energy that contributes to the universe's mass energy content and therefore to space-time curvature. Light connects distant events, making causality possible. Without light, the universe would be radically different, perhaps not capable of supporting structure, complexity, life, or consciousness. In this deeper sense, light creates the possibility of facts existing at all. It creates the framework, the space-time structure, within which definite events can occur and be related to each other causally. Light is not just the mediator between possibility and fact. It's the foundation that makes both possible. And there's an even deeper answer, one that borders on philosophy and poetry. Light, in its dual nature as wave and particle, embodies the relationship between possibility and fact. As a wave, light exists in superposition, spreading out, encompassing multiple paths and states. As a particle, light is localized, definite, factual. Light is both at once, always. It's the bridge between the quantum and the classical, between the indefinite and the definite. When we observe light, when we collapse its wave function and detect it as a particle, we're not changing light from possibility to fact. We're revealing the fact that was always latent in the possibility. The wave and the particle aren't separate things. They're two aspects of the same thing. Possibility and fact aren't separate realms. They're two perspectives on the same underlying reality. This is the profound insight quantum mechanics offers us. Reality is not either, or it's both and. Light doesn't turn possibility into fact by destroying possibility. It turns possibility into fact by showing us that possibility and fact are two ways of describing the same thing from different perspectives. From outside the system, before observation, we describe reality as a superposition of possibilities. From inside the system, after observation, we describe reality as a definite fact. But the underlying reality, whatever it is, isn't changing. Only our description, our perspective, changes. This is why different interpretations of quantum mechanics all work. They're all different perspectives on the same underlying mathematical structure. The many worlds interpretation says all possibilities are facts in different branches. The Copenhagen interpretation says observation turns possibility into fact by collapsing the wave function. Cubism says possibilities represent our knowledge and facts represent updated knowledge after measurement. They're all describing the same phenomena from different viewpoints. And light, because it travels at the speed of light, because it experiences no time or space, because it connects all the events it touches into a single timeless event from its own perspective, light transcends the distinction between possibility and fact. For light, everything is immediate, eternal, unified. The separation between possibility and fact is a perspective we have because we don't travel at the speed of light. But from light's perspective, there is no separation. So the ultimate answer is this: light doesn't turn possibility into fact because possibility and fact are not separate things. They're two perspectives on reality. Light shows us how these perspectives relate, how they transform into each other, how they're ultimately one thing seen from different angles. This is a deeply satisfying answer because it respects both the mathematics of quantum mechanics and the mystery of existence. It doesn't eliminate the mystery. It contextualizes it. Reality is mysterious, not because we don't understand the laws, but because the laws themselves tell us that reality is fundamentally perspectival. What's true depends on how you look at it, and light is the medium through which we look. So where does that leave us practically? What should you take away from this journey? First, reality is stranger than you thought. The solid, definite world you experience every day is actually a statistical average of quantum processes, a classical limit of quantum behavior maintained by constant environmental observation and decoherence. The definite world is real, but it emerges from an underlying quantum world that's fuzzy, probabilistic, and interconnected in ways that defy common sense. Second, observation matters. You're not a passive observer of a pre-existing reality. You're an active participant in the process by which reality becomes definite. Your observations, mediated by light, collapse wave functions and contribute to the creation of facts. You matter. Your existence has physical consequences for the structure of reality. Third, everything is connected. Through quantum entanglement, through the structure of space-time, through the light that connects distant events, through the shared process of observation and decoherence, everything in the universe is linked. You're not an isolated individual. You're a node in a vast network of interactions that constitute reality itself. Fourth, light is central. It's the mediator of observation, the definer of space-time, the creator of matter, the carrier of information. the bridge between quantum and classical, between possibility and fact. Understanding light is key to understanding reality. And fifth mystery remains. We've explained a lot, but we haven't explained everything. We don't know which interpretation of quantum mechanics is correct. We don't have a complete theory of quantum gravity. We don't understand consciousness fully. We don't know if there are other forms of observation or interaction we haven't discovered. The universe still holds secrets. But that's exciting. That means there's more to discover, more to understand, more to explore. And you get to be part of that exploration, not just as someone who learns what others have discovered, but as someone who observes the universe directly, who collapses wave functions, who participates in the creation of reality. You're not just in the universe. You're part of the mechanism by which the universe exists. Every time light enters your eyes, every time you observe anything, you're performing the fundamental act that turns possibility into fact. You're the universe observing itself, creating itself, understanding itself. That's not just beautiful, it's true. The physics tells us so. And if you internalize that truth, if you really understand it, it changes everything. You see yourself differently. You see others differently. You see the light around you differently. The next time you see a beam of sunlight streaming through a window, or watch stars at night, or simply look at your hand in lamplight, remember, that light is collapsing quantum superpositions, creating definite reality, connecting you to distant events, carrying energy that could become matter, experiencing no time or space, defining the structure of space-time itself. That light is the mechanism by which possibility becomes fact. And you, by observing that light, are participating in the most fundamental process in the universe. You're helping to create reality itself. That's the ultimate answer to our question. Does light turn possibility into fact? Yes, through observation, information transfer, decoherence, and the fundamental structure of space-time. Light is the primary mediator by which the indefinite quantum realm becomes the definite classical realm we experience. But more than that, light reveals to us that possibility and fact are not separate things. They're two perspectives on the same underlying reality, and we, through our observations mediated by light, get to participate in the transition between those perspectives. You are an observer. You are a creator. You are part of the universe waking up to itself. And light is your tool, your medium, your connection to everything that is, was, or will be. Thank you for taking this journey with me. Thank you for sticking with it through all the complexity and strangeness. You're part of a special community of people who aren't satisfied with easy answers, who want to understand reality at its deepest level. I appreciate every single one of you. If you enjoyed this, hit that like button one last time. Subscribe if you haven't already. And drop a comment telling me what your biggest takeaway was. What concept blew your mind the most? What are you going to think about differently now? I read every comment, and I love hearing how these ideas affect you. And remember, the next time you see light, really see it. Recognize what it is, what it does, what it means. Light is not just illumination. Light is reality itself, in motion, in transition, in the eternal dance between possibility and fact. Until next time, keep observing, keep questioning, keep exploring. The universe needs you. You're part of how it exists.